Hello everyone, and welcome all on Data Phoenix webinar. Today with us Leo Pekilis. He is chief scientist at Gradient, and we will speak about building time series fundamental models, present, past, present, future. So we will see all journey and what can be with this type of models. You can ask the question using Slando. The link is under the video, and we will be happy to answer for all your questions after Leo presentations. Also, don't forget to join our Slack channel where we can continue discussion this topic as well. So, Leo, your stage.
Yep. Thank you, Dimitro. Yep. As mentioned, my name is Leo, and I'm the chief scientist at Gradient. Gradient is an AI foundry that is building complex AI systems to automate workflows for enterprise corporations. And as part of that, one of the things that we've been particularly interested and excited in is time series, right? Time series are fairly ubiquitous all around businesses and industries everywhere. And so it stands to reason that a large part of any kind of enterprise automated workflow would at some point deal with time series. And so what I'd like to talk to you all about today is how we've been approaching time series and the analysis of time series from the perspective of deep nets and AI systems. So with that, I will take it away. There we go. The agenda that I'd like to cover today is threefold. Is written in the talk title. It's to talk about the past and what actually currently is the present in a lot of industries, which is how time series analysis is traditionally done and how that leads to a fragmented landscape and a bottleneck in analyzing time series data. Kind of the state of the art of the present, which are large time series models or LTMs, and how that presents a unifying solution. And then also end with talking just a little bit about what's on the horizon, which are multimodal LTMs. So that's incorporating other modalities of data, text, video, images, alongside time series data. And I really want to stress and get across the point that time series is another modality every much as important as all the other ones that have been kind of more prominent in the discussion, kind of like around large models. Okay, so touching upon the past and how time series analysis is traditionally done. First, to kind of reiterate the point is that time series really are ubiquitous across industries, especially over the past couple of decades. Many companies are now either data-driven or at least data-enabled, where our measurement of the environment around us has really unlocked many applications of time series kind of across the board, right? From predictive problems such as stock price prediction, to monitoring patient vitals in healthcare, to demand forecasting and optimization, and all the way through to weather modeling. And because the time series are now ubiquitous across a lot of different landscapes and industries, both the number of use cases and the number of solutions have grown quite a lot over time series analysis is at least a century old at this point. And so because there's a lot of different flavors, there's perhaps as many different ways of working on time series as there are applications. And okay. And what this leads to is what I like to refer to as an intellectual fragmentation bottleneck. Because the use cases have grown so much, and because time series data has now become so ubiquitous, it is starting to become more and more important to have complex solutions in order to get extra amounts of value from time series data. And so now currently we're at a state where task and domain specific time series models require a significant amount of expert knowledge and development time. And kind of the result of this is you have isolated efforts in time series modeling and analysis, maybe in different pockets of companies or industries. And first, this causes intellectual fragmentation, right? There's not, it is difficult to kind of like share ideas across areas, and also inefficiencies, right? There's perhaps many more ideas and use cases out there than there are time series experts to apply to all of these problems. And so to give a very quick kind of like review of the traditional way of approaching time series, there's been largely two types of approaches. On one side, you can think about statistical models. And here, for folks that have either an analytics or a statistical background, these types of plots are likely something you're very familiar with. And typically, the way that these statistical models work is you end up looking at a lot of plots, right? On the one hand, if you're trying to fit an ARIMA model, you might be looking at your particular channel of data and looking at autocorrelation plots to try to see how many lags of data are useful or predictive of future time periods. You may be looking at quantile plots to check the homoscedasticity or the normality assumptions of the time series, or whether it's stationary, and doing perhaps slightly more bespoke statistical inference, like these Ling-Box p-values and statistical tests, right? And kind of the overall sum of what this all means is that each one of these applications of time series is very bespoke to the particular task and problem, right? You have to repeat this whole process every time you want to look at sort of a new environment or a new task. Another class of time series models are local smoothing models. In a lot of ways, these have been kind of like the workhorse of short-term time series forecasting. They're models that I've used myself quite a bit in the past. And while they're great in predicting short-term trends, kind of as you can see in the plot to the bottom right, with the confidence intervals here, as soon as you go to forecasting more than 1 or 2 time periods into the future, you end up dealing with a whole lot of uncertainty. And so these kinds of models, even though they're fairly straightforward to apply to many different types of time series tasks, they struggle with long-term prediction. And also they don't incorporate any kind of changes in data trends. There's another approach to time series analysis, which has been slightly more recent or slightly more specialized, and that's to look at kind of like dynamical or state space models, and starting to get into neural models, maybe that are trained in a supervised way. And these models are often reserved for kind of more meaty tasks, maybe where the value of predicting a particular time series, maybe it's demand forecasting for a very large company, or something like that, or actually warrants spending a lot of time and resources in developing a model. Again, they're limited in their scalability and adaptability, because they require a significant amount of development time for each new application. And kind of the other side of this whole issue is the data issue. The larger and more complex the model, the more data typically is needed to train it in order for it to be effective at its task. And so when you have a specialized model that is kind of like task specific, that was only trained on one task, well, that really limits its applicability to industries or scenarios that are data rich already. And so you can't really apply these types of models to maybe like data poor regimes or areas where you don't have just vast amounts of time series data. And so that was kind of this sort of the state of traditional time series modeling and forecasting. And so currently where we are today and sort of where really just about a year or two ago, folks have started looking at the advancements that have been done in deep nets that have been applied to language modeling, and specifically the transformer architectures. Transformer architectures have emerged as kind of a unifying solution also to time series analysis, specifically because it addresses a lot of the pain points that I just described. All right, so to touch on each of those really quickly, transformer architectures, their whole point is to encode a lot of data, right? They're vastly over-parameterized with many parameters, and so they can encode circuits or kind of like latent features of knowledge to then enable zero-shot sequence modeling, right? They've seen a lot of examples of data in the past. They've encoded it in their circuits. And so zero-shot prediction is now possible. So you don't need the extensive or expensive domain-specific tuning. The self-attention mechanism of transformer architectures is able to capture long-range dependencies and latent features in time series data. So a lot of this kind of like latent feature space learning is already baked into the architecture. And kind of what this all means is that LTM's large time series models can generalize across industries to give them more accuracy and flexibility. To give a little bit of evidence into the rising popularity of these types of models, here on the left, I have a chart of just in the past few academic conferences, some at the end of last year and ICLR at the beginning of this year, and looking and counting the number of submitted papers, actually accepted papers, sorry, and breaking them up by papers that have talked about foundational models by modality. And yes, definitely kind of language models and image models kind of top the list and continue to top the list and have been growing at quite a rapid, exponentially actually increasing rate. But you can see that time series models, this last bar on the right here, have also been growing actually since year over year have actually been growing at a faster rate than language models, even though the overall absolute number is still quite small. And perhaps the other maybe even more telling part of the growing popularity of LTMs is looking at the various industries and various companies that have all developed or released their own version of a large time series model just in this year. Just in this year alone, we have models from the likes of Amazon with the Kronos model, Salesforce, Google. Very recently, Datadog also released an LTM, and Gradient is also on deck to release our own large time series model also this year. And there's probably one or two that I've missed in this list as well. Okay, so what I thought might be interesting to share is a little bit about how large time series models are different from large language models, and sort of the kind of main components that allow them to work and be effective, and in many ways be as effective as kind of traditional time series analysis approaches. The first and kind of main area of adaptation is in the representation of time series data. Um, Tokenizing time series is actually quite a difficult thing, right? If you think about tokenizing language models, I think we all understand human language and have a pretty intuitive feel for it, right? So human language is made up of words, and furthermore, you can break down words into components of words, right? Tokens, and that's a pretty natural breakdown and interface for then an artificial intelligence to be able to reason about human language. For time series, it's not quite as clear. And I think because of that, there have been a number of different approaches on how you start with a time series signal and break it down into digestible components for an AI model to deal with. These different approaches span from kind of maybe the most straightforward or first thing you might think about doing, which is patching. So you take a time series signal and you break it up into discrete components. Each of these components is then treated as a separate token for predicting future patches. And these can either be a fixed patch size, or kind of like more recently, folks have started looking into multi-scale patches. On the other end of the spectrum, you could treat each individual time point as a token, right? So now an LTM is not predicting patches or kind of like steps of time series signal, that they're literally predicting every single next point. And then to maybe reduce the cardinality of the representation a little bit, you can apply some kind of scaling or quantization on top of that. And that's exactly what the Amazon Chronos model did, where they tokenized individual data points. And then there's a third approach, which is one that we at Gradient have taken. And that's to kind of step back and look at kind of the source of the issue, which is that the language of time series, or the representation is maybe not quite well understood, and to try to really get down into the core of what are the atoms or the individual components of a time series that then you can use to compose and to create a signal. And so here is an image from a chart from one of our early works. And this was taking a specialized k-means algorithm to a large data set of different time series data, and trying to learn a dictionary of different signals. I believe here they were I believe they were a patch size 4 signals, and breaking down those patches into kind of their composable atoms that then you could put together to create any type of time series that the model has seen before, and then encoding that dictionary as tokens. Okay, so that's kind of like one place, and probably the most important part of how building a time series model is maybe different from a language model, and that's really understanding the vocabulary of what a time series signal is. A second important area is the time series exhibit both temporal and spatial dependence, right? That's kind of like the reason that traditional time series analysis look at all of these partial and autocorrelation plots, partial correlation, autocorrelation, is because time series tend to have temporal and spatial dependence. Well, it turns out the attention layer in transformer models is kind of a very natural way of dealing with correlation and autocorrelation. Because if you think about it, the way that an attention layer looks up relevant keys in a particular stream to a query is kind of exactly what you want in terms of autocorrelation, where if you take perhaps your multi-channel input and structure it all as one long stream of data, then you can kind of let the transformer model learn and adapt to decide what lags of both the time series signal and also related signals for multivariate data to attend to. And so, in a lot of ways, that means that really, again, attention is all you need for temporal and spatial dependence. And it's not fully that simple. It doesn't kind of like work straight out of the box. Um, you do need to update your attention architecture a little bit um, to kind of ensure that you still have the permutation, equivariance, and invariance that you do want among your multivariate ordering and indices. But those are fairly straightforward adaptations of regular self-attention. And then the other thing that you need to worry about is time leakage, right? You want to make sure that when you're training a time series model, that you're not inadvertently leaking information from the future, because if you're trying to forecast a time series signal going forward, the easiest way to forecast it is to already know what you're going to predict, and so that just requires a little bit more custom kind of like causal masks, and then sort of everything works out. Right, and so here's a chart or an example of how the folks at Salesforce have implemented attention-based temporal and spatial dependence using actually a layering of different positional IDs, both to have identifiers in the time domain and in the spatial or the variant domain. Great. And the final component that is required to train a large time series model is, of course, the data. Kind of the cost of being able to do zero-shot forecasting is that there needs to be a large amount, a ton of pre-training data to encode all the information that you need to do forecasting in the circuits of the large model. And so along that vein, at Gradient, we've put together a time series pile, what we call the time series pile plus, which is a data set of over 70 billion time series observations. It is building on top of the LOTSA data set that was put out by Salesforce earlier this year, which is 30 billion observations. And in order to enable any large time series model to have a range of kind of like robust applications to have seen a lot of prior examples of time series, we've made sure that the data set covers a wide variety of industries and applications. You can see a breakdown of the different domains in the table here on the right. It is definitely weighted towards industries and customers that Gradient kind of typically works with, but there's also a widespread, many domains that time series data is incorporated in. And we're also constantly updating our data set with additional sources. The most recent one that we've been looking at and looking into is adding clinical waveforms from the PhysioNet database. And while it's not currently open source, I do want to take this opportunity to mention that we do plan to open source the time series plus pile for the community very soon. And that's because Gradient itself has benefited quite a bit from the open source community in over the time that we've been around. And so we're very passionate about giving back to the community and feel like that everyone's sort of working together to improve these models is really the best way forward. Okay, so that is just a quick overview of sort of the current state of the art in how large time series models are built. Finally, I want to talk a little bit about the future, what's on the horizon, which are multimodal time series model. And so that's integrating multiple modalities, not only time series, but also bringing in text, images, and tabular data, for example. To give a taste of what sort of applications are possible with multimodal TSM, here are just a few different examples. On the one hand, you can think about enhanced forecasting ability, right? There's quite a bit of auxiliary data that can help you to forecast your measurements even better. So you can think about incorporating text information, maybe news articles or social media sentiment to improve the forecasting accuracy of, say, a stock price prediction or something like that. On the other hand, you can think about sort of a co-pilot-like time series analysis. So perhaps imagine using a natural language prompt to perform complex time series analysis. So this is stuff that Gradient has been particularly interested in doing recently because what it enables is sort of a much lower barrier to entry to doing time series analysis. And so here an example would be to pair a prompt such as forecasting next week's sales, take into account holiday season, with the actual time series of past sales, and then the multimodal TSM will take that prompt and the data to know exactly what is the signal that it should forecast and respond with. And then lastly, you can take kind of that translation in the other direction and think about an explainable AI solution where you start with a time series channel or time series data, and then you end coming out of the model a textual explanation or something that is more human interpretable summary of the signal. Okay, and to maybe touch upon that last point and expand on it just a little bit more, I wanted to share a recent example from a paper from a lab at CMU that we at Gradient do a fair amount of joint work with, and this is working on text summaries for ECG waveform data, right? ECG data is electrocardiograms, and electrocardiograms are a way for people to monitor, or for clinicians to monitor heart health without performing kind of an invasive procedure. And a lot of times what happens is you take an ECG reading and you get a graphic that's something like this one here on the left. And then the clinician or doctor has to spend time interpreting that signal, right? So for example, they take a look at a signal and they say, hey, the sinus rhythm position is normal, but maybe there's possible hypertrophy, right? And this takes away time from the doctor actually treating conditions or spending time with the patient, needing to read charts, but also can result in a non-standardized level of care, right? Not everyone is as skilled as sort of interpreting or being a time series data set whisperer, right? And so one thing you can think of doing is training a multimodal time series model to do this kind of summarization for you or automatically. And so the bottom row in this chart is an example of exactly that. This is a multimodal time series model that's trained to provide summaries of ECG data. And you can see here that a similar electrocardiogram was given to this model. And the summary that is spit out is, or the summary that it reported is quite similar to what a clinician could have or would have written. Okay, so this is still a very active field of development and an area where a number of folks including Gradient, are kind of heads down at work on. So I just wanted to kind of leave off with a few approaches and challenges for multimodal time series models. There are a few very promising approaches. They range from kind of the Q-former techniques, which take pre-trained models from different modalities. So say a pre-trained time series large model and a pre-trained large language model, and then uses a Q-former to create a learnable query token by aligning representations of time series and text. And then these learnable query tokens are then fed into a language model, which then uses those tokens as kind of the prompt to output a summary. Another promising direction is to move all that a little bit closer to the source and in a more unified way. And that's to, from the start, try to project the different modalities all into a shared representation space. And then train an end-to-end architecture on top of that to jointly predict or to jointly run inference, outputting both time series and text and image or video data. And so an example of a recent technique and model that does that is Meta's Chameleon paper that worked on this approach and trained an early fusion model for images and text. And you can think about doing something similar for time series and text as well. And then finally, another interesting approach are compression tokens. And that's a way of taking time series data, which can be quite high density, right, high signal, and compressing that into a more compact representation. And that enables longer and larger context inference or interaction with time series as well as other modalities of data. The two main challenges currently for multimodal time series models, they're both related challenges. It's mainly around the fact that there's just not a lot of data out there currently unlocked to train these models. I think with language and image and vision models, we've been pretty lucky to tap into the vast amounts of social media data out there to be able to help models learn at least an internal representation of how these different modalities interact. It's not as immediate to find similar data or time series plus other modalities. So that's an area that does need to be unlocked to really open up the floodgates for multimodal time series models. And then similarly, there's a lack of comprehensive evaluation benchmarks. And so something that we believe is until that those benchmarks do exist, the field for multimodal time series is going to be a little bit scattershot and maybe a little bit less congealed on sort of the architectures and approaches that work best. Okay, so that brings me to the end of what I want to talk to you all about today. Maybe the thought that I wanted to leave with is that time series are really the outputs of the measurement of sensors that are all around us, right? In a number of ways, that is the language of our environment. And human language is how people naturally interface, how we all naturally interface with each other. And so multimodal LTMs are a way to enable fluent communication with our environment.
Yeah, Leo, thank you for your very interesting overview. We have several questions, so let's start and answer for them. Do you think there will be a kind of general tokenizer ever for time series data, or it will always be use case specific?
Yeah, that's a really good question. I think the goal is definitely to have a general tokenizer. I think one of the challenges in identifying what a general tokenizer looks like is that time series data is not kind of like in human natural fluency. I think it was in a large ways for natural language and also in some ways for images too, maybe a little bit more easy to figure out like what a tokenizer looks like. For time series, it's a little bit less clear. I think there have been a lot of interesting directions and forays into different representations of time series data, right? So taking a look at Fourier transforms of data and seeing if that's a more applicable transformation and representation or wavelets. And I think it's definitely on the right direction, but it's not quite there yet. So that's currently an area of work.
Thank you for your answer. The next question, would sports predictions qualify as part of a time series?
Sports predictions as a part of time series? Yes, definitely. Yeah, I think sports and sports data is a fantastic area of both training data and use cases. Anywhere that you have metrics, any metric is a time series.
Yeah, next question about your future model. Will be some demo Hugging Face space for TSP
Time series pile. Yeah, it's a hard one to say. Yeah.
So yeah, how big is model? What hardware request?
Yeah,
for running this
all
model?
great questions. Yes, we do plan a demo posted for our time series models. So just as a quick point of clarification, the TS pile is the name of the training data set for the model. The model name itself will be something slightly different. And kind of a nice byproduct of time series models is they tend to be a bit smaller than language models. I think the typical small language model size is in the high billions or low tens of billions of parameter counts. That is already seems to be sufficient for even kind of like the biggest time series model. So while we don't have like an exact parameter count and model size right now, it'll probably be somewhere around there. So you can think about it as like running Llama 7B model is roughly the same amount of compute requirement.
Thanks for the insights. Moving on to the next question. Are there any semi-supervised pre-training methods for N-time series model different from LLMs, masked language modeling, and next sentence prediction?
Yeah, interesting. So I think I think it is a very appropriate kind of like parallel or analogy to make between masked language modeling and next sentence prediction and time series. I think what is currently a very reasonable and has been a pretty fruitful approach is to do a very similar thing, but instead of thinking about predicting the next sentence, you're maybe predicting the next patch in a time series or the next few time periods. So it's a very similar approach to how large language models are trained.
Yeah. What do you think about new methods like XLSTM, which promised better performance than transformers via linear architecture?
Yeah. So I think this is touching upon the fact that transformer models have quadratic complexity in the attention mechanism, and LSTMs, state space models like Mamba models, all have linear complexity in their attention. And so I think there is definitely applicability. I think you see the same trade-off where having the more powerful transformer models are able to capture more of that spatial and temporal dependence and able to handle kind of like more complex relationships between time series. Whereas the linear attention, they're able to maybe take in much longer time series with lower computational overhead. And actually, something that I think is like pretty interesting to look into is the combination of the two, maybe using the linear models to do a first stage of compression, or looking at linear models kind of like for the tokenization end, and then using kind of like the full force of the quadratic models to do kind of like complex attention across now the compressed time patches.
Thanks. Let's continue with the next question. What is your opinion on state space models from an industrial perspective? Do they align better with your domains than transformers?
Yeah, so I mean, look, I think in a similar way that if you take kind of the best authors in the world, or the best marketers, or the best kind of generator of social media, they're probably going to create content that is higher quality than currently what you can get out of a large language model. I think in a very similar way, if you take the most highly trained time series analyst and they create a state space Kalman filter model on top of a ton of data that's coming from, say, maybe it's on Uber data to predict the amount of demand for Uber rides globally, you're going to get a better forecasting model than something that you can get zero shot from a large time series model, right? So the best of state space models coupled with a human expert that actually knows how to train and run the model, and with enough data, you're going to do better. However, that is a very high resource cost that requires the value of the output to kind of like be proportional for that cost, which is exactly what's created this bottleneck of having many more applications for time series data than actually the resources to work on them. And so kind of the promise of these LTMs is to be able to take maybe not the most advanced use cases, but things that are sort of maybe like one or two steps down, and to perform across a very, very large variety of those, and do them maybe not as the best of the best, but still pretty well.
Thank you for your answer. The next question is, LLMs are already able to generalize knowledge across physical systems. TS models need to generalize across actual physical equations. Is that even possible?
Yes, I think again, I think it's a good analogy to language models, in that there's been a number of studies that have shown that language models, when they get large enough and are trained on enough data, they show emergent behavior, right? They are able to internalize kind of very deep and pretty complex templates to be able to do things like perform math or work on logic problems, and they know how to rhyme and have emergent kind of like task behavior. The analogy to time series is very, very similar. There hasn't been a lot of data or study here, but the idea is very similar, where if you have a large enough model and enough data, what the AI model or the deep net will be able to hone in on is similar types of very complex templates, which then you could very likely find analogs to equations. So by the nature of the fact that the model has a lot of capability to learn, and a lot of data is going into it, a lot of examples are going into it, it kind of backs out some of these physical relationships.
Thanks. Are video and audio a source of abundant and available time series data, or are they inherently different?
Nope, not inherently different. I think audio in particular is one that's very interesting, because not only does it exist as a analog signal, right? It's already as a time series, but there's quite a lot of data out there that is multimodal, right? So you have the audio signal, and you have the kind of the written text translation. So that's a pretty rich source. I think one of the areas of caution is that you don't want that to be your only source, because then you train a model that does speech-to-text translation, and models like that already exist. The idea here is to create a more general application, general purpose time series model. So you don't just want audio data, you want data from other domains as well.
One more interesting question. I work in financial services. Do you have any view on what DBase to start using to capture this kind of data for use in the future?
I'm going to guess that DBase is maybe a database. Yeah, I think the state of kind of like storage systems today is that it's quite simple and quite straightforward to capture gigabytes, hundreds of gigabytes, terabytes of data, and the architectures and data pipelines to transform that data are fairly readily available. And I think the application of take your favorite recipe from Hugging Face to do data transformation, and it applies in a fairly straightforward way to time series data as well.
Thank you. Our next question is, should a TS Foundation model be only trained on univariate data? Otherwise, how could it be used for zero-shot inference or retrained on different dimensions?
Yep. So no. It should be trained on both univariate data and multi-channel data. And the idea is, if you have a flexible enough representation where you can maybe concatenate all of your channels and then tell the model which parts of your prompt or your stream correspond to which channel. And then if the model has seen both univariate and multivariate data in the past, come inference time, it'll be able to do inference kind of like across both of those versions of problem, both univariate and multivariate data, and kind of like regardless of the number of channels.
We've covered all the questions we received. Here is the last one. How to tokenize TS data, considering each time step is only a number in univariate data, while for multivariate, how to generalize it to different dimensions?
Yeah, there's a number of different approaches to doing this, and I think sort of the kind of like the bet is still out as to which approach is going to be the most natural for, say, the language of time series. What I think, what I personally believe is the right way to tokenize time series data is really to look at to look at it from a representational learning perspective, and to try to break down or to suss out the individual components or the atoms of time series, or kind of like the dictionary of the vocabulary for time series that can then be composed to create any time series signal and to tokenize that dictionary. And so there's a number of approaches for how you can approach representation learning or dictionary learning. Kind of the example that we talked about, or that I talked about in the slides, is you can think about it as a specialized k-means type of approach, where you look at different examples of time series patches in the past, you break them down into groups of patches, and then those are the groups that you then that is a certain limited cardinality. Those are the groups that you then tokenize, and then come inference time, when you have a new time series, you effectively rebuild that time series from the dictionary that you've already learned. I think one perhaps analogous way of thinking about it is it's very similar to how compression works for JPEGs, where you create kind of like a dictionary of your patches, and then you reconstruct the compressed image from that dictionary.
Yeah. So the question is ended. thank you for all who was with us, who asked the questions today. Thank you, Lea, for this amazing presentation and overview. I hope for all our participants it was very interesting and useful. Thank you, and see you next week on next webinars.
Yeah, thanks for having me. Appreciate it.